Hello, and welcome to Matrices and Systems of Equations. My name is Tuesday J. Johnson. I'm a lecturer at the University of Texas El Paso and an assistant professor at Doña Ana Community College. This is for Math 1508 Pre-Calculus at UTEP. Chapter 8, Matrices and Determinants, comes to us from Larson's 10th edition Pre-Calculus text. Section 8.1, Matrices and Systems of Equations. So let's talk about it. Matrice, that's the plural of matrix. This has nothing to do with that Keanu movie from more than a few years ago now. A matrix is a rectangular array of numbers. It's like a table, only it has brackets around it. It's an ordered way to keep our coefficients and solutions organized and eliminate the need for actual variables as we're writing our systems of equations. So, how do we label these matrices? Well, if m and n are positive integers, an m by n matrix is a rectangular array with m rows and n columns. It's a lot like we talk about lumber, right? A 2 by 4 is 2 inches thick, 4 inches wide. M by n matrix, m rows, n columns. So here's the table type of form for it, but it has brackets around it, set it apart. And we talk about the first row, and so here we have 1, 1, first row, first column, first row, second column, second row, third column, and so on. The mth row, the nth column, so m rows, n columns. And when we're talking about the size of a matrix, we're referring to its dimensions or order. We'll always report it as rows times columns. So when we look at these, we have, for example, in example number 1, 1 row and 4 columns. It's a 1 by 4. Example number 2, we have 3 rows, 4 columns, so it's a 3 by 4. And example 3, we have 2 rows, 3 columns, and so we call the size of the matrix a 2 by 3. Alright, here's some facts about matrices now that we know about their size. So a matrix derived from a system of linear equations is the augmented matrix of the system. It's very important that our equations have to be written in standard form, a standardized form. That way we know the first column has all the x's, the second column has all the y's, and so on. The matrix derived from just the coefficients of the system, but not including the constant terms on the right-hand side of the equal sign, is called the coefficient matrix of the system. I'm not going to emphasize this very much. If you want to know more about these matrices, linear algebra is a class for you to take. It's a great class. So let's look at some of these augmented matrices. 1, 7x plus 4y equals 22, and 5x minus 9y equals 15. To write this in matrix form, notice that my x's come first, and then my y's, then my equal signs, and then my constants. So when I put this in matrix form, I can now ignore the plus, the equals, the x, the y, and I write down just the coefficients. In the first equation, I have 7, 4, 22. Second equation, 5, negative 9, 15. Where the equal signs is, a lot of times for augmented matrices, we'll put in this line to say, hey, look, here's the coefficient matrix on the left, and we've included the constant matrix on the right. We've augmented or put them together to make a system of equations matrix. If we have 3 equations with 3 variables, we will end up with 3 rows of our matrix and 4 columns, because we'll have the augmented matrix. So our coefficients are negative 1, negative 8, 5, and then my constant term 8. Coefficient negative 7, 0 y's in the second equation. If we're writing an equation, we don't have to put plus 0y. But when we write it in matrix form, we have to include the 0 as our placeholder to say, hey, there is something here. It just happens to be 0. Negative 15 is in front of the z, the negative 38, and so on. So we just take the coefficients because we know all of our x's are in column 1. All of our y's are in column 2. Z's in column 3, and constant terms on the right-hand side of our augmented line. Again, this second equation has no x's written, so I'll write 0, and then negative 25, 11, negative 5 to fill in the rest. Don't forget the zeros, they're very important. Not only do we need to be able to take a system and write it as a matrix, if you're given an augmented matrix, you need to be able to translate it back into a system. And you'll see why here in a few minutes. But for now, remember, if we're given variables x, y, z, and w, we're not going to need that. We want to write the system, everything in the first column, x, everything in the second column, y. I hit the augmented line, so I know I have an equal sign, and these will be my constant terms. So this says 7x minus 5y equals 0. Second row, 8x plus 3y equals negative 2. Let's do that again. Now we have 3 columns before the augmented line, so 3 variables prior to the equal sign. We'll use x, y, and z. 4x minus 5y minus z equals 18. Negative 11x. Now a 0 in a matrix I have to write, a 0 in an equation I don't. So I will say negative 11x plus 6z, and I won't even bother with the 0y, equals 25. Similarly, 3x plus 8y equals negative 29. I skipped the 0z because I don't need to write it. That's not necessary for an equation, but it is extremely important in the matrix. Okay, so when we were solving systems of equations, we had some steps to follow for Gaussian elimination. And elementary row operations are the exact same things, we just changed the terminology a little bit. When working with matrices, we can interchange any 2 rows. If I don't like what I have in my top row, I could take that whole top row, move it to the bottom, and put a different row up there. But I have to take the entire row, not just little elements of it here and there. I can multiply any row by a non-zero constant. This is the same as maybe multiplying an equation by the least common denominator, so I don't have to deal with fractions. And this is the key to our progress here. Add a multiple of a row to another row. So this is when we maybe multiply one equation by 2 and add it to a second equation so we could eliminate a variable. It's the same idea here, only we no longer have the variables that we have to deal with. A couple more terms here, and these are definitely ones you'll want to know if you're using graphing calculators. They'll help you out, or any computer-aided device. A matrix in row-echelon form, also known as REF, has the following properties. So any row consisting entirely of zeros occurs at the bottom of the matrix. Remember, we can interchange rows, so if something happens and they're not at the bottom, all we have to do is interchange and get them there. For each row that does not consist entirely of zeros, the first non-zero entry has to be a 1, and we'll call that a leading 1, and a lot of times in here, instead of leading 1, I will put quotes around the 1, we'll make it a 1. And for 2 successive non-zero rows, the leading 1 in the higher row is farther to the left than the leading 1 in the lower row. So that's row-echelon form, and it's a stair-step type of pattern that I talked about in systems of equations. I believe it was section 7.3 from this lecture series. A matrix is in reduced row-echelon form, RREF, if every column that has a leading 1 has zeros in every position both above and below that leading 1. So the coefficient matrix will only have 1s on your diagonal and zeros elsewhere if it's reduced row-echelon form. Whereas a matrix in row-echelon form will have 1s on the diagonal and zeros below, but other numbers possibly above the diagonal. So that's the difference between the two. Alright, so when using Gaussian elimination, the row operations that we just talked about, to obtain a matrix in row-echelon form or reduced row-echelon form, always operate from left to right, just like we read English, we read math left to right, by columns, using elementary row operations to obtain zeros in all entries directly below the leading 1s. In red, that's how extremely it is. It is extremely important to have an organized approach. You must know where you're going each time, or else you don't know where you're going to end up. Always left to right, top to bottom. So let's do an example. We're going to write the matrix in row-echelon form in order to solve it. So we're given this matrix, and it corresponds to some system, and it has x, y, z, equal sign, constant terms. Our goal is always to have a 1 in the upper left-hand corner. That's our first step every single time. Once I have a 1, I want zeros below it. So I have a 1, in quotes, in the upper left corner, so we make zeros. I'm going to use this 1 to eliminate and make zeros. So what do I add to 3 to make 0? I add negative 3. So I'm going to multiply a row 1 times a negative 3, everything in row 1 times negative 3, and I'm going to add it to row 2, so row 2, and I'm going to get a new row 2. Negative 3 plus 3 is 0, negative 6 and 7 is 1, 3 and negative 5 makes negative 2, and negative 9 and 14 makes 5. Notice, even though I used row 1 to eliminate to make a 0 in row 2, I always go back to my original row 1 with the quote 1, my leading 1 in that row and that column. So here's my new row 2 in blue. I want to eliminate this and make a 0 also. What do I have to add to negative 2 to make a 0? I have to add 2. So that tells me exactly what I need to multiply 1 by. I'm going to multiply 2 times row 1, add it to row 3, and when I do so, that's going to be my new row 3, and I put it in my new matrix, 0, 3, negative 5, and 14. So that's our first step, actually 2 steps. First step, make a 1. Second step, use that 1, that leading 1, to make zeros below, using essentially the elimination method. Now, this is the same matrix, I just took the colors out. We have a 1, we have zeros below it. Our next step is we want a 1 in row 2, column 2. Right? Row 1, column 1, row 2, column 2. We want 1s on the diagonal. So I already have a 1. I'm going to use it, always use our 1s, to make a 0 below. So what do I add to 3? In order to make a 0, I add negative 3, and that tells me exactly what to multiply by. Negative 3 times row 2, added to row 3, so 0, negative 3, positive 6, negative 15, and I'm multiplying row 2 by a negative 3. Add it to row 3, I'll end up with 0, 0, 1, negative 1. 0, 0, 1, negative 1. That's my row 3, my new row 3. Now I'm in row echelon form. I have 1s on the diagonal. I have zeros below. Other numbers above, we'll deal with those. And now, just like in systems of equations, we could go and back substitute. So I know that this says z equals negative 1. If z equals negative 1 and y minus 2z equals 5, then y equals 3. Check my arithmetic. Pause if you need to. And once I know z and y, I can back substitute. This is x plus 2y minus z equals 3. And I can solve to find the x equals negative 4. We found the solution to the system of equations using matrices. Alright, so another example. Again, we have a leading 1. I want to make zeros below it. In order to make the zeros below it, I multiply row 1 by the opposite of whatever I'm trying to eliminate. So I'm trying to eliminate a negative 3. I'm going to multiply positive 3 times row 1. Add it to row 2 to get a new row 2. 0, 1, 1, 2. Check my arithmetic. You can hit pause at any time. That's the reason I'm doing these videos. You can follow along, hit pause, rewind, fast forward when you get tired of hearing me talk, whatever it needs to be. So my new row 2. I want to eliminate a 4, so I'm going to multiply row 1 by a negative 4. And when I do so, I get a new row 3 of 0, 2, 2, 4, which I put here in row 3. Now my spidey sense is tingling here. I'm thinking, these look very similar. Let's see what happens. We have a 1, and we made zeros below it. We have a 1. It's nice when that works out. We'll get some examples where we have to make a 1 in a little bit, but it's nice when that works out. We want to make a 0 below it. So to make a 0, I'm going to multiply this 1 by the opposite. I'm going to multiply by negative 2. Negative 2 times row 2, added to row 3, my new row 3. Notice all zeros in the bottom row. Because it's all zeros in the bottom row, this is always true, right? 0 equals 0. You'll notice I've stopped putting in my augmented line. It's pure laziness. That's all it is. But this is a dependent system. 0 equals 0. How do we write the solution of a dependent system? So if we have the matrix on the previous screen, first of all, we're going to let z be a. So it's dependent. It depends on what you choose. And so we're going to put an arbitrary value. So z is arbitrary. Z is a. Equation 2 tells us that y plus z equals 2, but I know that z equals a, so I'll call that y plus a equals 2, and I could subtract a from both sides and get y equals 2 minus a. Now that I know that y equals 2 minus a and z equals a, I could go to the top equation. X minus 3y equals negative 7. But I know y is 2 minus a, so I substitute, distribute, and solve for x. X equals negative 1 minus 3a, so my point form would be negative 1 minus 3a is my x value, 2 minus a is my y value, and a is my z value. So for any z value you give me, I can find the y and the x that go with it. Alright. Now, use matrices to solve the system of equations. Use Gaussian elimination with back substitution or Gauss-Jordan elimination. The difference is Gaussian elimination will take us to row-echelon form, 1s on the diagonal, 0s below. Gauss-Jordan elimination gives me 1s on the diagonal and 0s below and above. So Gauss-Jordan elimination is reduced row-echelon form. And the answer to that, once you get 1s on the diagonal and 0s elsewhere, the coefficient matrix on the right will be your answer for x, y, z, w, what have you. Alright, so first thing I do is I put my system of equations in matrix forms, x, y, z, and constant terms, filling in the zeros where I have them. I have 0 x's in the second equation, 0 z's in the third equation, so a 0 in the second row and a 0 in the third row. So now, in order to make a 1, we either multiply or swap. There are no 1s leading any of these equations slash rows. So what I'm going to do is multiply 1/2 times row 1. Half of 2 is 1, half of a negative 1, half of 3, half of 24, and I did nothing to change the other 2. So to make a 1, the leading 1, we either multiply by a reciprocal or we swap rows. Swapping wasn't a possibility in this one, so we multiplied. With our new leading 1, we want to make zeros below it. We already have 1, so I only need one step. I'm going to multiply by negative 7. So negative 7 times row 1 plus row 3. Multiply all the way across. Add straight down to get our new row 3. I know, it has fractions. You can deal with fractions. When you have halves, feel free to use the decimal, that's fine. I don't like decimals in my matrices because they get lost. I don't write them dark enough, or they start looking weird and I have no idea what's going on. I use fractions more frequently. Also, if these were thirds instead of halves, the decimal would lead you astray the further you go. So use fractions as much as you can tolerate. Build up a tolerance for fractions. You're going to need them in your future mathematics courses. So we have a 1, 0, 0. I need to make a 1 here. Neither of these have a leading 1, so I'm not going to swap. I'm going to multiply by a half again, also known as dividing by 2. And that's the only thing I'm going to change is row 2, multiplied by a half. And now I need to make a 0 below it. In order to make a 0 below our row 2, column 2, 1, I'm going to multiply row 2 by 3 halves, add it to row 3, and that'll be my new row 3. Always, you are welcome to hit pause, make sure my arithmetic is correct. I will tell you, I've done this one several times, so I made sure it was right, but I encourage you to check it out. You get ugly numbers like that, you always want to make sure that we're going down the right path. So I have a 1 and made zeros below it. I got a 1 and I made 0 below it. I need a 1. In order to make a 1, I multiplied by a half in my previous 2 steps to make 1s. But think of it as the reciprocal. I'm going to multiply by the reciprocal in order to make a 1. Always. It's the multiplicative inverse. So when I multiply negative 45/4 by negative 4/45, I get 1. The nice thing is, when I multiply negative 135 over 2 by negative 4 over 45, I get 6. And we can breathe a sigh of relief because, okay, z is not a fraction. It's not some ugly, horrible fraction. Z is 6. When z is 6, we know y minus 1/2 z is 7. Go back to the previous slide if you need to see that equation. When z is 6, that makes y 10. The top equation says, the top row translates to x minus 1 half y plus 3 half z equals 12. Put in the y value of 10, the z value of 6. I end up with x minus 5 plus 9 equals 12, so x equals 8. And my solution, 8, 10, 6, not so bad, even though I had to use some fractions along the way. Alright, last example. So, we take our system of equations, 2x plus 2y minus z equals 2, x minus 3y plus z equals negative 28, and negative x plus y, notice no z's, so I'll have a 0 in there, equals 14. But as I'm writing in matrix form, I don't want to write the matrix and then say, oh, hey, look, I could swap. I notice that equation 2 has a leading 1, right? 1 is the coefficient of x. So I'm going to write equation 2 as my row 1. Then I just shift equation 1 down to row 2, and equation 3 stays in row 3. Swapping, or exchanging one row for another, is a great way to make ones if you don't feel like dividing. I could have divided by 2, that's fine. I would have made a fraction, but I could deal with that. Now I need to make zeros below, so I'll multiply negative 2 times row 1 and add it to row 2 to make a new row 2. I need to make a 1 here, but notice 1 plus negative 1. I can just take row 1, add row 3 to get a new row 3. But as I'm putting these in my matrix, notice I said new row 2 here, but I put it in row 3. Why is that? I know that I need to make a 1 right here. And if I need to make a 1, would I rather divide by 8 or divide by negative 2? Personally, I don't want to have to divide positive 58 by 8 and deal with that fraction. I would much rather divide by 2 and have an easy time finding my ones, easier fractions to work with. So even though this says new row 3, I put it in row 2. I swapped my answers because I was looking towards my next step. Once I have those swapped out and exchanged, to make a 1, I'm going to multiply row 2 by a negative 1 half. Changes the sign of everything. I left row 3 the same. Taking this matrix, going to the next slide. I want to make a 0 below, so I'll multiply by negative 8 times row 2 plus row 3 is a new row 3. Notice my 1's on the diagonal, 0's below. That's always our goal. Always left to right, top to bottom. Starting at the far left, make a 1, and then go down, make 0's below it. Down 1, over 1, make a 1, 0's below it. Make a 1, 0's below it if you need to. Now we know that z equals 2. We know that y minus 1 half z equals 7. So half of 2 is 1. Y must be 8. X minus 3y plus z equals negative 28. Substitute our values. We get x equals negative 6. Our solution, negative 6, 8, 2. This process is the same no matter how many variables you have. If you have 4 equations with 4 variables, you would just keep going. You would now make a 0 below, then make a 1, and continue with the exact same process. I hope this clarifies a few things for my students. Maybe you learned something new. I hope so. Thanks for listening.